We're going to talk about error. We're going to talk about the remainder today. We've talked about convergence intervals and how something is really good within a convergence interval, but outside of the convergence interval, you're going to have error. There's going to be a gap between these Taylor polynomials and Maclaurin polynomials we're creating and the functions that they're actually modeling. So we're going to be talking about the gap. That's what the error is that we're talking about. But before we talk about that, we have to define something called a maximum. They use capital M in the book, like a bold capital M, to talk about the maximum. So this is what we're going to define that as. All right, a function has a max bound M only on a closed interval okay, and so the closed interval would be from A to B if all f of x values are less than or equal to that maximum. So this is not like a new concept to have the max of an interval, but it has to be a closed interval, and we're defining it as this capital M or a bolded M. And so homework is going to start with kind of some easy questions, just having you practice identifying that. All right, so identify, and most of this is going to be common sense. Okay, identify the M for f of x on each interval. Okay. So just a couple of questions about that. If the first function I ask you about is 3 sine of half x, and the interval is from negative 4 pi to positive 4 pi, from your basic common knowledge of what sine looks like, what's the guaranteed maximum within any interval really of sine, knowing like how a sine wave shaped?
1 for this one.
Not 1 for this one.
3.
Okay, this one has an amplitude of 3. Okay, so because the behavior of this is going to be like that with an amplitude of 3, so we don't have to prove it or anything. Our common sense tells us that m would be 3, that all f of x values within the interval will be less than or equal to that number. Nothing will ever be greater than that. Okay, if we have a different function like x to the 4th minus 3, and the interval on that is negative 3 to 1. Again, we're using a little bit of our common sense. X to the 4th is a quartic. What is its general shape? This one's not going to have the little loop in the, but it looks like a parabola, and if we've got extra x terms, then it'll have the W shape. But this is just going to have the general form of a parabola. And so its maximum is going to be not at the vertex, because that has a minimum. So it's going to be on one of the sides. So we know that negative 3 to 1 is probably how these bounds of that are going to go. So by our knowledge of what the function looks like, because it's symmetric to the y-axis, we know that the maximum is going to occur on the left endpoint. And so then we can figure out, well, what is f of negative 3 then? So that would be negative 3 to the 4th minus 3. So that's 81 minus 3. And so we're looking at 78. And so the maximum for this is 78, which means all function values within that closed interval have a maximum bound of 78. Will never be higher than that. Okay, any question about maximums? Okay. All right, so we need to talk about that before we can lay the groundwork for what we're going to talk about in terms of error. The word they use is truncated error. In English, the word truncate means to cut something off. Okay, I'm just going to stop you here. That's to truncate something. We truncate when we round things. We cut it off at a certain point. All right, truncated error. Truncated error is the difference between the actual polynomial, or the function, sorry, okay, the actual function f of x and a fixed length polynomial which we defined last week to be p sub n of x. The difference between the two of them. And that is called truncated error. That's the words to describe it. So the absolute value of f of x minus p sub n of x. So the difference, so it is the absolute value when you're doing a difference. And then the subtraction between what the function actually is and versus what one of the polynomials would tell you that it was estimated to be, and how different are they. And these errors are going to be very, very small. We looked at convergence intervals last week when we were playing with the calculator, and we could see that we could go to many, many decimal places before we'd even find some error. Okay, so to truncate something, remember that f of x is estimated approximately equal to p sub n of x. Okay, those two things are approximations of each other. We are going to cut the polynomial off at k. All right, we're going to truncate the polynomial at k. So that means we're going to go out to the kth term, and then after the k, term k, where we're going to stop our polynomial, there's going to be everything else that we cut off, and we call that the remainder. So that's r of k. So the p of k is the truncated polynomial where you cut it off, and r of k is what we call the remainder. And that's still equal to, or approximately equal to, f of x. And so if we move the terms around, how would you get the remainder alone? Subtraction, exactly. Okay, so this is where the definition comes from. When we subtract f of x, or use f of x, and we subtract the truncated polynomial, that would isolate the remainder. And so it's the subtraction of the two. It's easier if I maybe show you an example. Okay, truncate the polynomial for the function f of x equaling 1 over 1 minus 3x at k equals 5. All right, well, we got to start the polynomial first. This is a geometric series. What's the first term going to be? 1. You can tell because a is 1 on the top, so the first term will be 1. And then what is the multiplier here to create this polynomial? Right? We have a sub 1 over 1 minus r, right? What's the r in this case? Okay, it's 1 minus r. So what is r, positive or negative? Okay, r is positive. Whoops. Okay, so there's your r. So the next term would be 3x. What would the next term be? 9x squared. And the next term would be 27x cubed, and then 81x to the 4th, and then 243x to the 5th, and then 729x to the 6th, blah, 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 on and on and on. All right, we are going to truncate this at k is 5, which means we're going to truncate it right there after the 5th power. So then the remainder would be starting with 729 and on forward, okay? So the r of 5 of x, the remainder is that way, and the truncated polynomial, p sub 5 of x is that way. Okay, that's just called truncation. All right, now we're going to continue the example. Now that we know that, the rest of the question would be like this. Determine an expression for the remainder to find error. So now we're going to isolate just the remainder. It's actually cooler than that. Yeah, but yes. Okay, the remainder for this problem starts with 729x to the 6th. And I've written out a couple of them. It would keep going with 2187x to the 7th, and then 6561x to the 8th, etc. Okay, that is where the truncated error part starts. The error and remainder are equivalent terms to each other. Okay, what can I factor out of that? What do they all have the same? They all have 729 x to the 6th. So if I factor that out, I'll be left with 1 plus 3x plus 9x squared plus, so I'm left, if I factor out the 729, I'm left with the original expression. And the original one came from 1 over 1 minus 3x. And so my overall remainder can be expressed as 729 x to the 6th over 1 minus 3x. So that is your expression for the remainder, which is the same thing as your expression for error. Okay, then you continue the same example once you had that, and it would be like part C. Limit the error to no more than 0.0001. So you take the expression you just found for the error, which is 729x to the 6th over 1 minus 3x, and you make sure that that is no more, okay, than 0.0001. I should have error's absolute value, so this is absolute value, so this is absolute value. So if you take the absolute value off, then our error bound would be between negative 0.01 is less than 729 x to the 6th over 1 minus 3x, which is less than 0.0001. And then I'll let you use a calculator to find that with a very small window. Okay, you'll put that polynomial, because you can't solve that algebraically very easily. And so you'll put that into your calculator. I would use 3 bounds, or 3 equations. I would put probably this in y1, and I'd put this in y2 and that in y3, and I'd look for the intersection, so where the y1 intersected. So basically you're going to have two horizontal lines with a very small window, and then your polynomial in the middle, which will intersect both of those lines, which is going to help you know what x is going to need to be bounded between. So x would then need to be bounded by the solution that you get when it intersects the upper limit of the error and the solution you would get on the bottom. And I did not write down what those are going to be. I wrote them down for this problem. Okay. Okay, let's try another one. Let's work with f of x to be the natural log of 1 plus x. And we're going to estimate the error for p sub 2. So we're going to truncate it at p sub 2. All right. So if f of x is the natural log of 1 plus x, then from our Maclaurin table, oh, and I didn't give you center. This is centered at 0. Centered at 0. Got to know that, so you know that you can use Maclaurin. So for Maclaurin, this gets us started as x minus x squared over 2 plus x cubed over 3. Okay, there's getting going. So we're going to truncate this at 2, so right here. So this part of it is your polynomial, p2, and this is your r2. So our remainder, the absolute value, so the error is going to start with if you can't factor out anything. Okay, we could factor out an x to the third, but that's not going to help me. I'm not going to end up with the same thing I had that I started with. Okay, so I could try it. I could factor out an x cubed. That's going to leave me with 1/3 minus 1/4 of x, which is not the same as what I started with in terms of my polynomial. So then what do? Here's where the idea of maximum comes in. How many terms are in a remainder? Infinitely. Which one of those terms is the biggest? The first one. Why? Because what happens to all the other terms as we go through a remainder? They all converge. So the biggest one is that, okay, well, these have to converge, right? These have to be convergent. Yeah, if it's divergent, yeah, all bets are off. Okay, but we have a convergence interval. It's centered at 0. Okay, so we know that we've got a convergence interval right now. So we're good. We're guaranteed on that. We're not going to be divergent. All right, so assuming that that one is the biggest, well, then all you got to do is focus your error on that one. Okay, that single one, we're going to focus our error just on that. Okay, so then we just got to go with what the third term would be. And we'll find the limit. I don't know if we're going to finish this, so I might take a couple problems off your homework. Okay, the third term of this series, say that you did not remember your Maclaurin, like you had a blank or whatever, and you couldn't come, could you come up with it by hand? The third term, you should be able to, right? What's the third term? It's going to be the third derivative of x times x minus the centeredness to the third over 3 factorial, right? You could do that, all right? And we want to find, so that's going to be what we're going to focus on in terms of our error. So what is the third derivative of this? I worked it out. The third derivative is 2 over 1 plus x cubed. And we've got times x to the third over 3 factorial. This is our remainder. So the absolute value, of R2 is equal to this. So they asked you to find an expression for the remainder. This is the biggest thing you have to worry about. You don't have to worry about anything else. It's just going to get smaller and smaller and smaller. So you focus all your energy on the big one. And then let's make that guaranteed to have an error, say, less than 0.0005. And they will give you that in the instructions. So what would you do to make sure that this would never be beyond, how many zeros did I write? 0.0005. So then you would solve that. Okay, I can simplify that. This would be 2x to the third over 1 plus x quantity to the third, and then 6, which means I could reduce that 5 and point negative 0.0005. And you'll do the same thing I was just describing as solving that between 3 graphs, 2 linear lines on a very small window, and then your polynomial in the middle to find the intersection of where you want your x to be.